seats. We're going to get started. Okay, so our first talk this morning is Stephanie Tonnesen. She is going to tell us about insights from simulations on gas content and star formation in satellite galaxies. Take it away.
Thanks. Thanks and good morning. First I want to thank the organizers for what's already been, it feels like I'm echoing, what's already been a really good, conference, and I'm really looking forward to the next 2 days. So I also want to thank them for inviting me to give this review on the insights from simulations on gas content and star formation in satellite galaxies. In order to attempt to fit within my 25-minute slot, I'm going to focus on cluster galaxies. Let's see. There we go. Okay. So, and also in an attempt to keep within time, I'm going to keep some slides in for background for students and for people who are interested in a lot more background than I'm going to give, but I am going to skip over several slides in the beginning. I'm going to start by orienting all of us with what large-scale simulations are telling us about the population of satellite galaxies in simulated clusters. And then I'm going to focus in on what small-scale, more idealized simulations are telling us about how environmental mechanisms, particularly ram pressure stripping, are affecting the gas and star formation rates in cluster galaxies. Along the way, I'm going to try to highlight where simulations are agreeing and where simulations are disagreeing so that at the very end, I can ruminate on what I think we need to do to continue to move the field forward and answer some of those open questions. So first, simulations are getting similar trends in the population to observations. So if we look at our left panel here, we can see that there's a higher fraction of gas-poor galaxies in simulated clusters. This is from the Yonsei zoom-in cluster simulations, and you can see that in purple in the field, there's very few gas-poor galaxies, whereas all the rest of the lines are showing cluster samples sliced and diced in various ways that show you that indeed there are more gas-poor galaxies in clusters. You can also see that there's a higher fraction of quenched galaxies in clusters. This is from a Denari paper, which is mainly on TNG galaxies, but here you can see lines from several different simulations. In the center panel, you can see the quenched fraction of centrals, which increases as you increase galaxy mass, as we would expect. And if you move to satellite galaxies in the right panel, you can see that particularly at low mass galaxies, the quenched fraction jumps by quite a bit, again, in line with what we expect from observations. So simulations are generally getting what we expect. And we can also look at other measures that are generally agreeing with the trends from observations. But I don't want to say that simulations are doing everything perfectly, and I don't think that anybody expects that to be the case yet. So although our overall trends are the same, in the details, we aren't generally, cosmological simulations are not getting perfect matches with observations. So here I've thrown on some observational points that I grabbed from a Bahe paper in those dots, and you can see that actually most of the cosmological simulations are over-quenching low mass galaxies in massive clusters. And if I have time, which feels really unlikely, I will circle back to this and talk about how some of the answers later in the talk can maybe help us solve this discrepancy. Okay, so now that we are all together and we know that simulations are indeed predicting that galaxies and clusters have less gas and tend to be more quenched, let's see what simulations are telling us about the environmental mechanisms at play driving this quenching. And luckily, I don't have to go over all these mechanisms because Luca did a fantastic job earlier. You can split mechanisms into gravitational mechanisms and ICM gas mechanisms, and they might affect galaxies in different ways. But what seems to be coming out of cosmological simulations is that ram pressure stripping tends to be the most common process removing gas from cluster galaxies. And this is shown in several different ways, which again, I'm just going to skip through, but leave the slides for you if you're interested. You can study this because in simulations you can track galaxies. You can actually measure, are galaxies just losing gas or are they losing gas and stars? They tend to just be losing gas. You can also not just track galaxies, you can track particles in simulations. And you can find that the particles that leave galaxies tend to leave along a stream like a ram pressure strip tail. You can look in great detail at the phase space of your simulated clusters. And you can see that where ram pressure stripping is strong, your gas fraction tends to be low. But just like we've been hearing with observations, simulations are not finding that environmental mechanisms are acting singly. They are acting in concert. And in this nice paper by Antonino Marasco, he actually looked to see how the strength of different processes varied for galaxies that were losing gas. And although he also found, hopefully I'm right, Antonino, tell me at coffee, not now if I'm wrong, he found that although ram pressure stripping was the most common mechanism stripping gas from galaxies, if you looked at the moment before galaxies became completely stripped of their gas, the strongest process tended to be satellite encounters. So yes, multiple processes are acting in concert. However, I think that if you want to really understand how environmental mechanisms are affecting the gas and star formation rates within galaxies, you want to start as simply as possible and really try to focus in on what an environmental mechanism is doing to the remaining gas and stars in a galaxy. And then layer on complexity so that you can refine your understanding. And so for that, I tend to use wind tunnel idealized simulations to study ram pressure stripping. So the pros here are that they're controlled and tunable. I can put exactly the galaxy that I want in exactly the wind that I want, so that I can really say, how does wind angle, how does ram pressure strength affect the gas and stars in a galaxy? They can be less computationally expensive. Instead of simulating a whole cluster or 100 megaparsecs of the universe and having to try to understand what's happening to galaxies within that cluster, I can instead focus my resolution on a single galaxy and then blow a wind through that galaxy to mimic its orbit through the cluster. Of course, if you want, you can spend all that computational power that you've saved by highly resolving your galaxy, which is a nice way to really focus on, for example, different phases of gas. And of course, as I already mentioned, the cons are that you don't have the cosmological context and you rarely include multiple processes. So keep those in mind. Now with that, we can take a look at these simulations to try and answer a few questions. First, does ram pressure stripping affect dense gas? We actually already got an excellent introduction to this by Luca, and the jury still seems to be out. There was a nice conversation by Luca and Bianca in the question section where we heard that in some cases dense gas seems to be enhanced and in some cases it seems to be depressed. Well, we can look at dense gas in wind tunnel simulations. And so these are results from a simulation of mine in 2009 where I compared the time evolution of dense gas in a series of simulations with different ram pressure strengths. So at the top, you can see the strongest ram pressure, and in the bottom, you can see the weakest ram pressure. The dashed lines are looking at isolated galaxies, so galaxies that aren't being affected by ram pressure wind. And the solid lines are looking at cases where the galaxy is being stripped by a wind. And you can see that there's a really strong trend with ram pressure strength. In our top panel, the isolated galaxy has much more molecular gas, or dense gas, sorry, it's not actually molecular, I don't have dust in chemistry, dense gas than the ram pressure stripped galaxy. But in the bottom panel, ram pressure stripping actually seems to have more dense gas, indicating that strong ram pressure is either destroying or stopping dense gas from forming, and lower ram pressure seems to be inducing the formation of dense gas. A key caveat here is that these are constant ram pressure stripping winds, and so looking at this in detail with a full orbit would be extremely interesting. More recently, a student at Columbia University, Jingyao Zhu, has in fact looked at a galaxy, an LMC-like galaxy, that's orbiting within a increasing potential. And so here's a 45-degree wind going through a box, and she actually studies the gas density and stellar surface density of these galaxies. And so as this galaxy is being stripped, she can actually plot the gas surface density. And so the gray lines are showing you the isolated galaxy at the same time as the yellow lines are showing you a galaxy that's in about a strong group cluster medium, intergroup medium. In addition, the solid lines is showing you the leading half of the galaxy, and the dashed lines are showing you the trailing half of the galaxy, which I've shown pictorially. And you can see that there's an enhancement of sigma gas, and that enhancement is symmetric in the center of the galaxy. And so this is actually indicating that there is mass transport, and so there's an inflow of gas towards the central region of the disk if it isn't stripped. And I'm going to circle back and talk more about that in a few slides. We can next see how does ram pressure stripping affect the star formation rate. And this is motivated by some really great observations by Benedetta, which maybe she'll be talking about later, that show that ram pressure stripping can in fact enhance the star formation rate of galaxies. So first we can ask, do simulations find star formation rate enhancement? And in the left panel here, I'm showing you the largest suite of ram pressure strip simulated galaxies that I could find from TNG 50. The points are all different jellyfish or ram pressure stripped galaxies. And you can see that most of them lie below the blue line, which is the TNG star-forming main sequence. However, there are a few points that do seem to have enhanced star formation rates. If we instead look at more idealized simulations, if you compare the black line, which is an isolated galaxy, to the colorful lines, which are various ram pressure stripping profiles, you can see that in most cases, ram pressure stripping is leading to star formation rates that are either quite similar to the isolated galaxies or lower. However, there are cases that are usually short and mild where you are getting ram pressure stripping enhancement of star formation. And so now that we're kind of armed with this knowledge that we can get enhancement of star formation rates, let's see when that actually happens. And I would say that simulations generally tend to agree that the wind angle has a large effect on when the ram pressure stripping can enhance star formation rates. If you have an edge-on wind, you're much more likely to enhance star formation. These are wind tunnel simulations by Nina Akerman, who's talking next, and where she's looked at a Milky Way-like galaxy in a cluster environment. And this is in general agreement with most work that has looked for this effect. However, we aren't in agreement when we try to think when, in terms of the orbital evolution of a galaxy, ram pressure can enhance the star formation rate. There's a lot of work that shows that star formation rates are enhanced at about pericenter, which you can see in this TNG sample with these points above the dashed line. But there's also a lot of work that shows that star formation enhancement can happen quite early in an orbit. So I think the jury's still out on this one, and a lot more work needs to be done to figure out degeneracies with inclination angle, galaxy mass, as well as orbit. Now, we can also look in detail in simulations at exactly where is there enhanced star formation in stripped disks. And again, this can be motivated by observations. This is another paper by Benedetta where she finds that star formation enhancement can occur throughout the disk and disks of several different masses. And so now we can look, where is star formation in simulated stripped galaxies? And here I'm showing you one of the more dramatic examples from my paper in 2012, where in the left you can see that the total amount of star formation rate is depressed in this ram pressure stripped galaxy. The red line is below the black. But if you look at the right, you can see that if I focus instead on the central region, there is actually an enhancement of star formation. So this is also usually found in simulations, although I do note that there's a simulation that finds star formation enhanced only in gas that's about to be stripped. Now, Jingyao Zhu in her 2023 paper looked at this in detail, and she finds that the star formation rate surface density very closely tracks the gas surface density that I showed you before. So the star formation rate surface density is enhanced in the center, and it's enhanced symmetrically. So then she looked a little bit more closely, said, why is this happening? And this is happening because there is dense gas mass transport in galaxies that are being stripped. So here you can see a narrow slab of a galaxy that's being stripped, and there's an edge-on component to that wind. Gas that's rotating into the wind shows you velocity vectors that are actually pointed radially inward, because that gas is being slowed down in its orbit and falling to lower radii, whereas the gas that's rotating with the wind at the outskirts tends to be removed. And so this generally leads to an inflow of gas towards the center, this large-scale mass transport. Jingyao also measured this by looking at the mass flux through a cylinder centered in the central regions of this disk. And although this is a busy plot, and I invite you to both read her paper and look at this in the PDF, for now I want to focus on the solid lines, which are measuring the radial inflow of gas. And you can see that the colorful lines, which are the ram pressure stripped galaxies, tend to show more radial inflow than the solid gray line, which is the isolated galaxy. So there's this radial flux of gas inward along the disk plane, which is giving us higher sigma gas and higher sigma star formation rate. So this is a lot of my take of what is happening. So I want to also let you know that there are works that are still arguing for local compression being important in inducing star formation rate. This is some nice work by the Tigris team, which Robert first introduced on Monday. And here they've blown a wind through this incredibly small box. So they can't find mass transport because of the size of their box. But they do see that initially, as the ICM sweeps through this box and pushes the ISM through the plane and out of the box, there is some local compression, which leads to short-lived and very mild star formation rate enhancements. So both of these may be in play in enhancing both the dense gas mass and the star formation rates in stripped galaxies. Now, I want to keep on moving even closer to the center of the disk and ask, could this inflow reach a central black hole? I think we're going to hear a little bit about observations that seem to indicate that AGN are more likely to be found in ram pressure stripped galaxies. So in her Milky Way wind tunnel simulations, Nina looked for the amount of mass in a 500 parsec, very small sphere in the very center of her Milky Way galaxy. And here we're looking at the cold gas mass over time. Again, our black line is the isolated galaxy, and our colorful lines are the ram pressure stripped galaxies. And you can see that in most cases, before the galaxy is completely ram pressure stripped and for hundreds of millions of years, there is more gas in the very central region of this galaxy. And so then she said, why is this happening? What possible reason could you have for an effect in 500 parsecs when the galaxy is being stripped from the outside in? And so she looked at several reasons. She looked to see if it was fallback of stripped gas. I'm not going to bore you with that. The answer is no. Then she looked to see if mixing of non-rotating ICM with the rotating ISM could cause angular momentum loss and lead to infall of gas. This was the answer I was expecting based on previous work, but when she actually carefully measured the fraction of mixed ICM within the disk, she found that it only could account for about 10 to 30% of this measured inflow. And so then she went and she calculated all of the torques on the galaxy on these central gas cells from gravity, so gas and stars, and also from local pressure gradients. And indeed, she found that torques were quite strong even in these central regions of the disk. Of course, ram pressure leads to gas asymmetry, particularly when there's an angled wind. And so this gas asymmetry can lead to increased torque and changes in angular momentum. In addition, there's local pressure gradients that can lead to strong torques and change the angular momentum of this gas. And so we think that together this does lead to a nice picture of ram pressure stripping affecting the very central regions of galaxies and perhaps leading to inflow to a black hole. Now, again, I don't want to say that this result is the only possible result. There's other reasons that you could get disk inflow. For example, if you have a flared disk, you could get oblique shocks from the ICM hitting your disk, and those oblique shocks could lead to gas reaching the center of your disk. So I think this is another case where more simulations that I think are going to confirm Nina's work are needed. So I've been talking a lot about how ram pressure affects the gas and stars and maybe feeds the AGN in the center of galaxies. But there are lots of processes in play. So can the internal process of star formation feedback help ram pressure to strip gas? And the first and one of the few works that's really focused on this, I think, was by Yannick Bahe looking at the gimmick simulations. So he was able to actually track particles that were stripped from galaxies. And in the top panel, you can see the lines show the fraction of ISM gas loss from particles that have not been affected by feedback. Whereas the bottom panel in the dashed lines is showing you all of the ISM that has been stripped by a galaxy, including fountain flows that have then been swept away by ram pressure. So, particularly in low mass galaxies, he is finding that ram pressure is sweeping gas directly from the disk equally to fountain flows being swept from the disk for the total gas loss from galaxies. Nina also decided to tackle this question in her highly resolved wind tunnel simulations. And so for this, she compared the stripping rate of two galaxies, a radiatively cooled galaxy with no star formation and feedback, and a galaxy that has radiative cooling, star formation, and feedback. And here you can see that when we include feedback, she does indeed get these beautiful fountain flows moving away from the disk. But just like we've heard all week, there's very little mass in these fountain flows. So when she measured the stripping rate between these, the solid line with star formation, the dashed line with radiative cooling, focus on the colorful lines, she found that stripping rates were extremely similar in these two cases. Although intriguingly, at early times, radiative cooling only seemed to be stripped more rapidly. And so she decided to take a closer look at the disk. In the top panel, you can see that the radiatively cooled case has very high density regions that are embedded in extremely low density regions. Whereas when we include star formation and feedback in this massive galaxy, you tend to smooth out your gas density distribution. And she quantified that on the right, where you can see that radiative cooling only has a lot of gas at low sigma gas. So this is looking at the gas surface density of these galaxies. And so as ram pressure begins to sweep gas away, that extremely low surface density gas can lead to a slight enhancement of the stripping rate without feedback. So in general, Nina's results are in line with Yannick's results, which showed that although fountains could be important at low mass, they don't seem to be important at high mass. So I think more work kind of looking at multiple masses is in order here to understand that interplay. So I don't have a lot of time. You can read the general agreement later. Who cares about what we agree about? Instead, let's look at the questions we still have to answer. So first, does ram pressure directly compress the dense gas in a galaxy, or are we talking more about mass transport through the disk? Well, I think that we got to go both observationally and with simulations to answer this question. We need more resolved H2 and H1 observations so that we can really try to understand why Luca's tending to see less H2, why the GASP team is tending to see more H2, and try and combine that with different masses and orbits. Then I think that we need a lot more high-resolution full disk simulations so that we can really see the compression that the Tigris simulations are actually able to see at the same time as seeing the mass transport that full gas disk simulations are able to see. And it'd be great if we could get some dust chemistry in our simulations as well so that everybody would believe we're really forming H2. Then, under what circumstances, particularly that orbital question, will ram pressure enhance star formation rates? And I actually think here that most work has got to be done with simulations because simulations actually have the full orbital history of galaxies. So I think we've got to do targeted searches and really try to dig into cosmological simulations and understand what's happened to galaxies. I'm like my last minute. But in order to believe those results from cosmological simulations, we've got to tie this to our wind tunnel simulations, which can actually resolve high-density gas, get to those densities of H2, rather than use kind of subgrid modeling to determine H2 fractions, and try and test our subgrid physics and see if changing our star formation model would actually affect how star formation rates change given different orbits. The question of whether ram pressure can lead gas inflow to a central black hole, I think, again, we got to tackle in both directions. Observations, I think, we've got to keep on working to see if we can actually find some smoking gun evidence of inflow to the central black hole. Simulations, we've got to actually include self-consistent black holes and feedback in these simulations, and it would be great if we could actually run some of the simulations that have super resolution near that black hole so we can get a lot closer than that few hundred parsecs that Nina was able to believe. And then finally, how does feedback interact with ram pressure? Well, I couldn't think of a good observational one. I'd love to hear your answers over tea, but for simulations, I think we actually need to do a good job in field galaxies. Okay, we've been talking a lot about the mismatch between simulations and observations, so let's get our measurements of the CGN correct with feedback. Then, I think, as I said before, I think we need to try and test this connection in lower mass galaxies where we expect feedback can have push out a little bit more mass from galaxies. And I'll just leave you with the fact that I think that we can really tie together different scale simulations to use the detailed mismatches in cosmological simulations and what we understand from high-resolution simulations to figure out what subgrid physics needs to be updated in those cosmological simulations. Is it that there's not enough dense gas in simulations, and that's why low-mass galaxies are being overstripped? Is it because feedback is too strong, and so all of those fountains are being overstripped? Is it because star formation rate threshold is too low, and so star formation is using up too much of the gas? These questions can be answered by combining multi-scale simulations. Thank you.
So in your last part about the fountain not being important for the stripping, does the orientation of the galaxy matter? So if it comes in almost edge on, for example.
Great question. So Nina looked at that too, and I didn't have time to show, but actually most of the stripping that happens in the edge-on galaxy is because of this is along the edges of the galaxy. So with your gas that's orbiting with the wind in the disk plane, that can get accelerated and leave the galaxy. Because the fountain flows, at least in Nina's simulations, have so little mass, even though that is getting swept away, it's a small fraction of the total mass loss.
But it should be 10% of the mass in the disk that is in this extra planar proportion. So I'm surprised that you say that there is little mass. It's not negligible.
Okay. We can look in detail at the exact amount of mass. The other thing that's happening in the edge-on case is there is a little bit of a residual bow shock. And so some of the very nearby fountain flows are able to actually return to the disk as you move further back in the disk.
Thanks, Stephanie. Just to follow up on this, does this depend on the intensity of the wind?
Yes. So that's another thing that we have to think about. So particularly, I think, in that kind of orbital question, I think it's key to actually try and test, does the strength of the wind matter, or does the gradient of the wind matter? So whether you have a plunging orbit or a more circular orbit, I think that's a really big deal. If I'd had 2 hours, I would have talked about some work that I did that shows that actually I think the orbit is really critical, more so than the peak, because, well, like I was showing, at weak ram pressure, you can get excess high-density gas. And so if you move that gas to high densities, then by the time you hit your peak, it's harder to strip. And so I think there's a lot of nuance in that question.
Thank you. I'm wondering whether CGM is included in the wind tunnel simulations nowadays, because like when the H1 disk is stripped, we have thought that molecular gas are also affected. So similarly, when the CGM hot gas halo is stripped, it would also, we can find some signatures of the H1 disk.
So in what I have shown you today, there wasn't CGM included. There are kind of 2 hot-off-the-presses papers, one by Jingyao Zhu, where she was looking at the CGM around satellites in the Milky Way, and one by Ratali Ghosh, where she was looking at the CGM around more massive galaxies. The upshot of Jingyao's paper is that the CGM is stripped almost immediately and has no effect on how the ISM is stripped. Okay. So that's why I didn't focus on it here. Ratali Ghosh also finds similar results, although she does find a little bit of a stripping delay. And so we're going to talk a little bit more to see what the differences are in our simulations there. But my take is that if you're getting to stripping of the ISM, CGM's gone.
About the results that were shown by Goller et al. 2023 for the main sequence, if actually you look at the star formation histories of the single galaxies, many of those show a very short burst of less than a gigayear. So probably it's in the definition of the star formation rate that burst is diluted in the definition, and so they see globally a lower star formation rate. But on very short timescales at the very beginning, also in TNG there is a short burst in many cases. So that's, I think, very interesting.
Yeah, that is interesting. Maybe I can put a lot on the spot, and he'll talk about it on Friday,
Okay.
or we can attack him at tea.
Okay.
Yeah. Okay.
No, thanks. What is, how do, I think Italy Gauche finds that if you have CGM, then the galaxy will feel a bit less from pressure at the beginning. So that could make the galaxy be stripped a bit smoother. That's an interesting possibility. Yeah. Thanks. Okay, hello. We can now relax for a bit. I just have a few introductory slides, and then 2 slides with figures, and then we are done. Okay, AGN feedback and affecting gas stripping. You might be wondering, what's the connection here? Why do we want to study this, and what's going on? Also, this is an early work in progress, so. First of all, from the observations, we know that AGN can be found with a higher incidence in pressure stripped galaxies than they are in regular cluster galaxies. This has recently been confirmed on a big sample of galaxies that includes not only our GASP galaxies, but also many jellyfishes from the literature. In the GASP galaxies, AGN-driven outflows, AGN feedback have been identified in several jellyfishes. And finally, as Stephanie gave a nice overview, in my own simulations, I found that RAM pressure can push the gas to the galaxy center, or more broadly speaking, RAM pressure stripping can result in more gas accumulating in the center, cold gas, that is later can be available to feed the black hole. So, this work, however, was done on a suite of simulations that did not include black hole and AGN feedback. So now I would like to come back to this problem and with an improved model. Again, I'm not going to go into details of my simulation setup since Stephanie talked about the general idea of internal simulations. What you need to know is that I have stellar formation and stellar feedback models at all times. I basically model a massive galaxy falling into a massive cluster with a varying RAM pressure strength, so the RAM pressure gets stronger with time. And they have 2 types of simulations. One is a fiducial galaxy, which I call no wind. So it's not subject to RAM pressure stripping. And one galaxy is subject to RAM pressure, but only face on. I call it wind 0. Now to the AGN model, which consists of 2 parts. There is a black hole and there is the AGN feedback. The black hole is always fixed in the very center of the galaxy. It doesn't move in the galaxy at all. Well, it's convenient because the galaxy itself is fixed in the simulation box, and its initial mass is 10 to the 7 solar masses. I have 2 types of black hole accretion physics, two accretion models. One is a classical von Hoyle model, I call it BO, and one is the mass flux of cold gas to the galaxy center, which is CG. So I have these simulations run parallel. At all times I have simulations, I have Bondi no wind, Bondi wind 0, cold gas no wind, cold gas wind 0. I also have a control simulation which doesn't have a black hole and AGN feedback, call it SF. Speaking of the feedback, it's always the same. It's represented by mechanical jets that are aligned along the z-axis, and the jets deposit momentum into the surrounding gas. So this video nicely shows how the jets are deposited periodically. The color bar is velocity, so that the red color is the outward velocity, you can see the jet, and the blue is the infall back onto the galaxy. Let's first begin by looking at the evolution of a no-wind galaxy. Instead of showing you how the black hole grows with time, I'm going to show something else here. Every time a black hole accretes gas, we store a bit of that accreted mass to be later deposited as a jet. When this accreted mass accumulates to 10,000 solar masses, a jet is deposited. This is exactly what is shown here. This is the stored mass as a function of time. What you need to know is that every time the line drops down, it means that the jet has just been ejected. So here, this is Bondi no wind. It has deposited 4 jets on the course of the simulation, 600 million years. This is called gas no wind. To say that it's different, it's an understatement. Jets are deposited as often as 10 million years sometimes. And while I could go into detail of why this happens, I think and whether we should change the model or not. What I want to focus on right now is the window of opportunities that is opened for us. We can study how the jet deposition affects the galaxy. So will the galaxy care whether the feedback is ejected every 200 million years versus every 10 million years, or will it not? To see just that, here I'm showing the star formation rate as a function of time in the whole galactic disk. So the black line here is the star forming no-wind galaxy, and you can see that almost immediately after the disk has settled down, the star formation rates in the two galaxies with the black hole are much lower compared to the galaxy without the AGN feedback, which tells us that feedback acts to suppress star formation. I find it interesting that although there is a general trend that star formation rates are still growing in the simulation, the difference is almost always constant. It's about 2 times, and it happens throughout the whole of the disk. Now, let's look at the 2 colorful lines, and we can see that they are remarkably similar. So it doesn't really matter how often the jet is deposited. The galaxy doesn't care. It just the feedback just suppresses star formation equally. Now let's move to the face-on-strips galaxy. I'm showing here the same figures. The gray area here shows separates the time before the ramp pressure. So wind hits the galaxy at 300 million years, and we model the effect of ramp pressure for only 300 million years. It's again the same general trend here. Bondy wind zero accretes far less than the cold wind zero. That's why the jets are deposited less often. On the other hand, I find it surprising that although the Bondy doesn't accrete gas for the first 150 million years, by the end of the simulation, the black hole in the Bondy wind zero is more massive than the black hole in the Bondy no wind, which means that the galaxy subject to the black hole in the galaxy subject to ramp pressure has accreted more mass. And this yellow line here stops at, it's not finished because I'm still running the simulations, but I'm 100% sure that this result is going to be different for the cold gas wind zero. Now instead of showing the star formation rates as a function of time, I want to show something else. This is the stripping rate according for star formation. It basically shows it basically measures how much gas is stripped at each point of time, how much gas just is removed from the galaxy. So look at the black line here, which is star forming wind zero. It has the initial high peak of the stripping, so a lot of gas is stripped immediately after the wind hits the galaxy, and then it just as rapidly falls down. On the other hand, the two lines representing the black hole galaxies with the black hole, they also have this peak, but it's not as high. And after the peak passes, they actually stripped a bit faster than the galaxy that doesn't have AGN feedback. And so the general trend seems to be that these galaxies are stripped more smoothly. Galaxies with the black hole, galaxies with the feedback are stripped more smoothly. Looking at that again at the colorful lines, we see that although the Bondy wind zero doesn't eject any gas in the first 150, doesn't eject any feedback in the first 150 million years, well, the cold gas wind zero in the same period of time has ejected several jets, and not only that, but actually there is ejected almost at the same time as when the wind hits the galaxy. The stripping rate seems to be unaffected. These lines are virtually indistinguishable, which seems to point out that the feedback does not simply impede or assist stripping, which reminds me of my previous work that Stephanie mentioned, where I was looking at the effect of stellar feedback on the stripping, and it also turned out that the answer was more complex than we would expect. So I will leave you with these simple conclusions and a nice video which shows on the leftmost panel the stellar feedback and galaxy fountains active, and on the other two panels we just have the jet being deposited. So thank you.
Thanks. Really nice stuff. I wanted to ask a clarification question. So this threshold you have for ejecting jets, does that also set the amount of momentum or energy that you're injecting into the jet?
Yeah, it's always the same though. So because the velocity is constant, it's 4% of the speed of light,
Okay.
and the jets are deposited every time once we cross this 10,000. So it's always more or less the same.
So one of the things we see in simulations when you look at the models for AGN feedback, especially in the kinetic mode, is that this burstiness or the amount of energy per injection event can have a very, very strong effect on how good this feedback is. So generally, you have two models, but both of them have the same energy input or
Yeah.
momentum input.
Yeah.
So it would be interesting maybe to see changing this parameter, how much that would affect the importance of the AGN on the stripping.
Yeah.
Or what do you think about that? I mean,
Well, of course, this is kind of the first work, and I think we can always increase the complexity of the model. This is also just the jet, right? It doesn't have the radiative feedback, which, but this, well, I don't think we need the radiative feedback because it's more for more for like quasars. We're not going to get a quasar out of an precious deep galaxy. But yeah, just tackling. Changing a bit the jet model, yeah, sure. I think it would be interesting.
thank you.
Other questions? Way in the back.
Hey, I just want to wonder, I saw that your resolution in the simulation is quite high given the
Yeah.
scale at which accretion is happening. So do you think we can learn more about accretion onto supermassive black holes by trying to push the resolution in those simulations to sub-parsec scale?
Yeah, absolutely. Like Stephanie said, it would be cool to have the hyper-resolved simulations. I don't think we can resolve the whole galaxy disk to sub-parsec resolutions, but we absolutely should resolve the inner, 100 parsecs into sub-parsec. That's what Angel Alcazar does. With the fire simulations, it's really fantastic work. But it's also here with the 40 parsec resolution, you can simulate the millions of years. With the sub-parsec resolution, you will only get a few years maybe, maybe a million year. I'm not sure. So we should do it, yes, but there is also time restriction, as in like human time.
Thanks.
We have time for one more quick question. I have a question. Is there any particular observation you would like to see focused on to kind of help interpret your simulations?
Well, again, it would be cool to actually measure the influx of gas in the center, but from so if you could see the how radially gas moves into the center. I understand. It would be best if you could do it like even the galaxy is face on, but I know that we can't measure velocity like this from the observations, or it is tricky. So maybe when the galaxy is a bit inclined, but yeah, that would be. So we could actually see how the gas spirals and whether we have enhanced. If you have statistics from precious deep galaxies and regular cluster galaxies, and we see whether these inflows are enhanced or not.
Let's thank Nina again. Okay, our next speaker is Georgia Peluso. She's going to tell us about gas phase metallicity of local AGN in the GASP and MANGA surveys.
Okay, thank you. Hello everyone, I am Georgia Peluso. I am a postdoc working at INAF Brera in Milan. And in the presentation of today, I'm going to show you this work about the gas phase metallicity of local AGN and the role of ramp pressure stripping in it. This is a work done in collaboration with the GASP team, and in particular with my PhD supervisors Bianca Maria Poggianti, Alessia Moretti, Mario Radovic, Benedetta Vulcani. So, let's start with a very general introduction about this topic. So, first of all, the gas phase metallicity of local AGN have been measured by previous works, but regardless from the galaxy environment. And also discrepant results have been found. Indeed, some works find that the nuclear regions of AGN hosts are less metal-rich than those in star-forming galaxies, while other works find the opposite result, which is that the AGN hosts are more metal-enriched than star-forming galaxies in their center. And the first result could be explained by a strong AGN feedback that quench the star formation in the galaxy circumnuclear regions, halting the metal production and the consequent ESM enrichment. I want to stress here that for AGN feedback, I mean AGN-driven outflows in the galaxy disk and not a jet along the x-axis. While the other result could be explained by many hypotheses, among which, for example, a top-heavy MF star formation in the accretion disk, or dust disruption, which release metals into the gas of the Broadway region, and then also AGN-driven outflow can enrich the gas in the narrow-ray regions and surroundings. The aim of this work is to explore, to study the role of the environment, and in particular to investigate the interplay between the AGN activity and the ramp pressure stripping phenomenon in shaping the gas phase metallicity of galaxies. Indeed, the previous works have shown a connection between these two phenomena, as Poggianti et al. 2017 and Peluso et al. 2022 found an enhanced AGN fraction in jellyfish. In particular, the ramp pressure stripped galaxies have an AGN fraction of 51% according to this work, which is higher than the 19% found in galaxies undisturbed by environmental effects and in the same bin of mass. An hypothesis is that, as you have seen in the previous presentation, that the ramp pressure stripping is able to trigger gas inflows, which eventually reach the galaxy center and light up the supermassive black hole. And simulations confirm this, as in Akerman et al. 2023. On the other side, the AGN feedback, the AGN-driven outflows can work in synergy with the ramp pressure stripping to quench star formation in galaxies. Actually, some works, both observationally and theoretically, have found evidence for this process. And in particular here, I show simulations by Ricarte et al. 2020, in which they predict the star formation history of two galaxies falling into a cluster. And the blue curve represents a galaxy without a black hole, while the red curve represents a galaxy with a black hole. And at this time, the two galaxies are experiencing a strong event of ramp pressure stripping. And it is very clear that the star formation quench way more rapidly in the case of the galaxy with the black hole, rather than the case of the galaxy without the black hole in this case. So the idea, the interpretation, is that the AGN feedback redistributes the gas from the inner regions to the outer part of the galaxy, and then this gas can be more easily stripped by the ramp pressure stripping. So under these assumptions, the star formation quenches more rapidly, the metal pollution stops earlier, and for this reason we expect that ramp pressure stripped cluster galaxies hosting an AGN should have a lower metallicity with respect to a control sample. To test this scenario, we build up a sample of ramp pressure stripped galaxies using the GASP survey. We all know what is GASP, so I will briefly remind you that the spatial resolution of this observation is 1 kiloparsec. These are pretty massive galaxies with up to 10 to 11.5 solar mass. And here you can see a collection of 12 galaxies observed by the program, and in particular in white you can see the stars. while in orange you see the H-alpha emission, so the emission of the gas. And so you can see that in these galaxies the stars are mainly undisturbed, while the gas distribution is highly disturbed. And this is a clear sign of ongoing ground pressure stripping. So among the GASP sample, we selected 48 galaxies showing clear signs of ground pressure stripping, and among them we find 11 AGN, galaxies hosting an AGN according to the BPT classification. 6 are CFET, and in red you can see the emission, while 5 are liners, and the emission is in green. Also, the liner galaxies have an X-ray point-like source overlapping the optical center, which is consistent with the emission from AGN activity. Then we also wanted a control sample of galaxies with similar properties than the ground pressure stripped sample, but not affected by environmental effects. And because of this, we use the MANGA survey, and we select star-forming galaxies, so with a high specific star formation rate, with late type morphology, and located in low mass halo, which means that we consider them to be located in the field, and so presumably not experiencing the ground pressure. To find the AGN, the criterion was to classify the emission within 3 arcseconds from the galaxy center, and to state if the ionization is mainly due to the stars or to the AGN. So here in this case you can see that the spaxels are, for example, are classified mainly as AGN in the BPT, and so this galaxy was indeed considered an AGN host. Finally, we also wanted to compute the gas phase metallicity, and to do that we needed to use an indirect method. Indeed, auroral lines are too faint in both the GASP and in the MANGA surveys, so we build up photoionization models using the last updated version of the code Cloudy, assuming ionization from stars, from an AGN, or from a contribution of both. And with these models we reproduce a set of emission lines and emission line ratios, and among which the oxygen-3 over sulfur, nitrogen over sulfur ratio, which coupled together are able to distinguish very well each model without degeneration between the parameters. Also in this case the models perfectly overlap the observations, as you can see here, and this is important because we also use the code nebula base to compare the models and observations in order to constrain the ionization parameter and the metallicity inside each spaxel of any given galaxy. And at the end, this is what we find. This is actually, these are the spatial, we obtain in this way the spatial areas of the metallicity maps of these galaxies, from which we extract the median metallicity inside the 2 different extraction apertures. The yellow aperture is scaled with the galaxy size, and so with the galaxy mass. However, in some cases, this aperture can contain a non-negligible fraction of star-forming and composite spaxels, and so we also define a green aperture, which is fixed as a radius of 1 kiloparsec, as I remember that the spatial resolution of this observation is nearly 1 kiloparsec, and is always dominated by the AGN emission. In this case, however, we consider galaxies, as you will see better later on, with a similar stellar mass, so that the final estimate of the metallicity does not depend on the portion of the galaxy covered by the fixed aperture. Okay, first of all, these are the results. We find that there is a hint of a relationship between the stellar mass of the host galaxy and the AGN metallicity, but this is weak. And presumably this is a consequence of the fact that the AGN are hosted only by the more massive galaxies with up to 10 to 10 solar mass, and so the mass range spanned by this relation is limited. Also, the distribution of the ground pressure stripped galaxies is statistically undistinguishable from the distribution of normal galaxies, meaning that with this kind of diagrams we are not actually able to spot this expected decrease in metallicity, because overall the AGN host resulted to be more metal-enriched than star-forming galaxies, regardless from the galaxy environment. So this is true for the cluster sample and the field sample as well. Here you can see also the star-forming galaxies, color-coded according to their star formation rate, so that you can see that on average the spread along the y-axis anti-correlates with this quantity in agreement with the fundamental mass-metallicity relation. Also, in agreement with previous findings, we find a plateau around 10.5 solar mass, and the blue dotted line is the fit of the star-forming galaxies, and the gray points, which are the AGN hosts, lie on average above the star-forming mass-metallicity relation within the error bars. The only two exceptions are these two galaxies, which are jellyfish, but these are also peculiar objects, so for now we consider them to be outliers. However, these also outline how it is important to enlarge the sample of galaxies, and in particular of the RAM pressure striped galaxies, in order to assess in a more robust way, statistically significant way, these kind of results. So, in this context, I want to quickly advertise this work, which is still in preparation, in which we developed a set of calibrators to be applied on the star-forming, composite, and NGN regions. These are basically very simple equations which describe the surface you can see here in these plots that can reproduce the metallicity estimates performed with the nebula-based analysis, which instead involve complex photoionization models, a Bayesian code, and so on and so forth. So this new toolkit of calibrators will be a much cheaper method in terms of time and computational power, and so this is why it is well suited to be applied on larger data sets, so stay tuned for future developments. Coming back to the mass-metallicity relation, and with this slide I will conclude, the results are also independent from the extraction apertures, since the same trend qualitatively hold also when using the green fixed aperture of 1 kiloparsec. As I was saying before, in this case we divide the galaxies into stellar mass bins, and inside each bin we compute the median AGN and star-forming metallicity, finding again that the difference is always higher than 0. So the AGN host resulted to be more material-rich than star-forming galaxies, regardless from the environment and the extraction aperture used to extrapolate the nuclear metallicity. With this I conclude. I will take questions.
Questions?
So this is very nice. I like your conclusion. I agree with it. But I was curious. Have you looked at how the metallicity changes with radius in the AGNs and star-forming galaxies?
Yes, so this will be the future work. There will be a paper about the metallicity gradients and how, in particular, we observe that this enhancement is limited in the nuclear regions, actually, of the AGN, because we compare the metallicity in the center and with the metallicity in the disk, in the galaxy disk dominated by star formation. And we see that actually the enhancement is within 0.3 effective radius, so it's very close to the nucleus.
I have a question, and maybe you said this and I just missed it, but did you account for, your galaxies that are living kind of in clusters have maybe been cut off from some fresh gas accretion, and so maybe their metallicities are a little bit high from that, and then when you compare them to your control sample, that might already result in higher metallicities than you expect. Was that?
You mean, if I understand correctly, that the stripping may change the metal content in the galaxy, so I'm...
No, just living in a cluster in general could be cutting off fresh gas accretion and change the metallicities.
Okay, in this, I think that the best answer is this one. Like in this, the star-forming galaxies are also RAM pressure, and so in cluster and in field. And in this case, you can see that this distribution, there is no how can I say, like here the only difference is the environment, okay? So if the environment is inducing a change in the metallicity content, I would expect to see something different between at least the star-forming galaxies, and I don't see that. Also, we are looking here, at least here, at the very nuclear nuclear regions. So, for example, the stripping or the environment is affecting maybe more the outskirts or not the very nuclear regions.
All right, let's thank our speaker again.
Okay, so now we have the poster session, so please, the poster presenters, just line up in alphabetical order. And then you have 2 minutes and you will hear my ringtone.
Giusto? Così con la freccetta.
E va a tutte? Non è
Sì,
per
mi sembra che va bene, ho provato prima.
L'hai provata prima?
Fai tu? Quindi aspetta che mi lavo dal microfono.
Devo girare le slide.
Beh, sono solo 2, quindi
Ma poi perché te le devo girare io? Però
posso andare? Ok. Hello everyone, I'm Alessandro Bianchetti. Let me actually fix this. Thank you. I'm Alessandro Bianchetti. I'm a PhD student at the University of Padova, and I'm working under the supervision of Professor Giulia Rodighiero and Professor Ed Elson at the University of Western Cape in Cape Town. And I've been working in the past year in comparing and combining the MIGHTY and Chile survey and performing a stacking experiment on them and trying to extract the scaling relation stellar mass versus H1 mass using the both of them, and using spectral stacking, meaning that we're stacking spectra extracted from information from optical catalogs. And the interesting thing, if you look at the big plot, is that we do extract a scaling relation which has a slope which is compatible with scaling relation in the local universe and with the only available result at a higher redshift, which is the scaling relation extracted by Chaudhary and collaborators in 2022, redshift 1, implying that the evolution of the scaling relation, if well described by a power law, is encoded rather in the normalization that in the model itself. And one other interesting thing to focus on is that this growth in terms of H1 seems to be slower than the one for which we have evidence for in other works for the molecular gas. And this is also interesting. Simulations do agree with the evolution seemingly encoded in the normalization, while under-predicting in general the content of H1, at least with the reference simulation I took, neutral universe machine. And also there's evidence for a band model implying that a scaling relation is probably not best described by a single power law, but maybe we need more than that. And I think I'm done, so thank you.
Okay, hello everyone, I'm Alessandro. I work at the Observatory of Padova. So, in the past years, thanks to the new incredible radio telescopes such as LOFAR and Meerkat, we are observing that many satellite galaxies, both in clusters and groups, show radio continuum tails. And here you see some of the most beautiful examples, but currently we know more than 170 galaxies with this kind of feature. What is the origin of radio tails? Unsurprisingly, is around pressure stripping. The same process that removes the interstellar medium from the stellar disk, producing the very famous tails of ionized plasma, can remove also the non-thermal components of the interstellar medium, so magnetic fields and relativistic electrons, which then produce radio continuum emission via synchrotron radiation. In our work, we wanted to use the properties of synchrotron radiation to try to constrain the dynamics of the outflows. Basically, the idea is that the property of the radio continuum tails in terms of length, projected length, and the flux density decline with the distance are set by the velocity of the outflow. The faster the outflow, the flatter is the flux density decline. And so we quantify with this behavior with a model, And then we test this model on 7 galaxies in that galaxy cluster there, which is Hubble 2255. The results are really interesting because, as you can see below, we are able to actually reproduce both the flux density decline and the spectral index decline, basically the evolution of the synchrotron spectrum with the distance from the disk with this model, and constrain the velocity of the outflows to be of the order of hundreds of kilometers per second. So my take-home message is that radio continuum observations can help us understanding the dynamics of the outflows induced by run pressure stripping, and so with the SKA we'll be able to repeat this kind of analysis for thousands of galaxies. Thank you.
Hello everyone, I'm Pomyeong Lee in Gasi, South Korea. The degree of environmental effects on galaxies could be different in various clusters depending on the physical properties of a cluster, various clusters such as dynamical state and cluster mass. So consequently, it's expected that the properties of a molecular gas on average and the star formation history can change in individual cluster. Therefore, several systematic sea observations for nearby clusters are required to study environmental dependency of the molecular gas and star formation properties. So being most massive and relaxed system within a 50 megaparsec, the Hydra cluster is a good target for this study. Using the Akerman compact array, we carried out 12 2-to-1 imaging observation for 50 massive Hydra galaxies that have H1 detection in the Wallaby project. In our ALMA synergy project, we would like to investigate environmental effects of the Hydra cluster on the physical properties such as H1, H2 gas and star formation of the member galaxies. Ultimately, we aim to quantify differences in the degree of environmental effects on the cluster members by comparing nearby galaxy clusters. Here is one example, and this is research 1 is undergoing active ramp strip in the Hydra cluster. In the left figure, the CO gas and HO gas are shown in color scale and contours. You may already notice that both the CO and H1 gas distribution are highly asymmetric due to the ramp pressure. In addition, the locally strong CO emission and NUV emission are found along the compressed H1 region where ramp pressure stripping acting on. These results suggest that ramp pressure can affect the diffusion and dense cold gas phases and as well as the local star formation activity. And also my poster includes a comparison of global properties between the Hydra and the field galaxies. If you are interested in these results, please come to see my poster. Thank you.
So hi, my name is Veronica Lora. I'm working in UNAM in Mexico City, and I come from the field of dwarf galaxies in general. Some of them are really dark matter dominated, and some are like lacking total dark matter like DDGs, like these tidal dwarf galaxies. So when I went into these jellyfish galaxies from all the GASP group, I read that they were finding along the tentacles of the jellyfish galaxies star formation that could be really massive as 10 to the 7 solar masses and have radius of 0.5 kiloparsec. So I went into the TNG simulations to see, what I wanted to see is if I could find a larger object, more in the range of dwarf galaxies, 1 kiloparsec of half mass radius. And we did in the tip of one of the tentacles. So what is important about this is that it's 10 to the 7 solar masses, is bound, is self-bound, has 2 10 to the 8 solar masses of gas, is young, metal-rich, and it doesn't have dark matter by construction. So this would be like a new kind of dwarf galaxies, like I said, a second-generation dwarf galaxies, more in the sense of TDGs, and could have like a range of mass and radius from ultra-compact dwarf kind of mass and radius to standard dwarf galaxies. So thank you.
Hello everyone, I'm Luca. I'm a first-year PhD student from University of Zagreb, and for my PhD I'm investigating this beautiful lopsided galaxy that is interesting because it is affected by both ram pressure and tidal interaction. So what I did currently during my PhD is that I investigated the Hubble Space Telescope images of this galaxy to investigate how the stellar population distributions are affected by those two effects. And here you can see the RGB image created from those different Hubble filters. The blue colors are younger stars, and the yellow colors are for older stellar populations. And you can see how the younger stellar populations are moved more towards the center. And you can see that also on these, this plot on the left, which show also these different stellar populations. And what I did also is that I sliced this galaxy into 8 different regions and then investigated the intensity profile. And on the left graph you can see the impact front with the dense medium that it is affected by the ram pressure. And you can see these different Hubble Space Telescope filters or the stellar populations on the left graph. And on the right graph you can see how the disk radius is changing across these 8 different regions. And if you have any more questions, please feel free to ask during the break.
Hi, I'm Daniele Mattolini, a PhD student from Trento University, and I work at a charity observatory with Stefano Zibetti and Annarita Gallazzi, using stellar population in the local universe. In this work, we revised the scaling relation from Gallazzi et al. 2005, and we improved them both on the models that we used in the stellar population synthesis. We updated the base ingredients for simple stellar population synthesis and composite stellar population synthesis, but we also included improvement in the data, meaning that we used a statistical correction to obtain a complete and volume-limited sample, but we also considered the correction for the aperture effect calculated by Zibetti et al. In preparation. And in the plots we can see the comparison between we can see the effect of these changes in the orange box. We can see the comparison between the scaling relation, the mass age and mass metallicity for the old version of the model, which is the one used by Gallazzi 2005, and the new one. And we can see that the improvement caused the formation of a bimodal distribution in the mass age plane and a shift towards higher metallicity in the mass metallicity plane. While in the purple box we can see the effect of the improvement in the data using a given model, in this case the updated one. And we can see that in the mass age plane we have an enhancement of the bimodality, given by the fact that the galaxies move from the old sequence to the young one. And in the mass metallicity, we see a mass-dependent decrease of the metallicities. These are the main takeaway from this plot, and if you have any question, you are free to ask and see my poster. Thank you.
Hi everyone, my name is Rossella Ragusa, and I'm currently a postdoc at TINAF Capodimonte together with Amata Mercurio. There is not enough time to go into detail about why it is really important to study the outskirts of galaxy clusters at intermediate redshift, but let me just say that since the galaxies in these regions are experimenting in fall and are so approaching to such a dense environment for the first time, to analyze the outskirts in the massive clusters can give us fundamental indication about the impact of the environment on physical properties of the galaxies. And to this aim, and following the photometric work done by Estrada et al. 2023, we analyzed the outskirts, I mean the region well beyond the cluster core, of MAX J0416 by using the data from A omega spectrograph. And in this work, we collected around 150 new confirmed spectroscopic members in the region between 2 and 5 virial radii that enlarge the already existing spectroscopic catalog from MUSE and VMUS. In particular, we found that around 60 of these galaxies are located in 3 overdensity regions plus filamentary structure found by Estrada et al. 2023, confirming the preprocessing scenario in which these regions are actually 3 subgroups that are experimenting the infall in the cluster. If you are curious about our work, take a look at our poster and don't hesitate to ask me or Amata for further information. Thank you.
Good morning. I'm Okan, PhD student from NLJ Japan. So I'm working on empirical model of chemical evolution of galaxies based on universe machine. So I calculate the metallicity evolution using the constraints of star formation rate and gas mass from universe machine and neutral universe machine, and with parameters of the fraction of metals that distributed to the H2 and H1 regions, and we search for the parameter space of these FH2 and FH1 to match the mass metallicity relations in star forming regions, the H1 regions, and CGM. And we found that this fraction that metal distributed to either the H2 or H1 is increased with halo mass, and there's increasing trend towards high redshift. But this is can be explained by the deep potential depths of at fixed halo mass. So if we plot this fraction as a function of circular velocity, which represents the halo potential depths, there's no redshift evolution. So it may indicate that outflows are determined by the depths of gravitational potential wave. So if you are interested, please talk to me. Thank you.
Hello everyone, I'm Umima Osman. I'm a postdoc at Trieste Observatory, but I'm presenting some of my work that I did for my PhD. So my work mainly focuses on our theoretical understanding of how dust influence galaxies evolution, so things like molecular hydrogen formation, chemical enrichment, thermal properties of the interstellar medium. So today I'm focusing on photoelectric heating, which is a process involving the interaction between far ultraviolet photons and dust grain surfaces. So what happens, electrons are ejected from the surfaces of grains, and then they restore the energy or the kinetic energy they have into the gas through collisions, and the result is a heat up of the gas. So here I'm presenting our results of hydrodynamical simulations of Milky Way-like galaxies. On the left, I have the phase diagrams of 2 sets of models. The top is with gas fraction of 0.1, and the bottom is with gas fraction of 0.5. So we can see how the photoelectric heating actually shifts the properties of the interstellar medium towards the upper left corner of the phase diagram. And these actually have implications and consequences for the star formation activities in these kind of simulations. And this is what I show in the bottom for the star formation rate time evolution. And those are also different sets of models with different gas fractions. We also find that photoelectric heating changes the mode of clumps formation, and this is what I show in the surface densities on the right. So I have the gas surface densities as well as the stellar surface densities. And we can see that when we have the photoelectric heating switched on, which are the model on the right, the clumps tend to form through violent disk instabilities. And once we switch photoelectric heating on, then on the right or on the left, the clumps tends to most likely to form spiral armed fragmentations. So photoelectric heating has a quite influence on those kind of galaxies when it's present. And just a bonus, we see also enhancement of gas outflows when we switch photoelectric heating on. If you're interested, please find me. Thank you.
Okay. Good morning, everyone. So, as previously mentioned by speakers earlier this week, the H1 or neutral hydrogen thickness of galaxies is quite a crucial thing to understand to really grasp the star formation mechanisms and stellar feedbacks and also other galaxy properties and galaxies. So usually those authors use like a single component model, although observations show that an extra planar gas, also known as thick disk, exists for those in observations. So it bears the question, is a single component enough to really characterize the H1 content in galaxies? And what would be the implication of star formation and also stellar feedback in a multi-component scenario? So to tackle these questions, we tried to measure the thickness of 4 edge-on galaxies from the Mongoose survey. And our early observations show that we have a good support for a multi-component disks. And I only have 2 minutes. I don't want to spoil everything. So if you are interested more in our results, my name is Nutainara Nevarmina. I'm a master's student from the University of Cape Town, and I invite you to go take a look at my poster, or you can talk to me over the coffee, dinner, or lunch. Thank you.
So, good morning, everyone. My name is Vicente Salinas. I'm a PhD student at Chalmers University of Technology, and today I'm going to talk to you about a work that was mostly done back in Chile at Universidad de Valparaíso, and it's a study about the tail directions of optical jellyfish galaxies. Now, we know that broadband optical images only show the tip of the iceberg when it comes to ramp pressure stripping, only showing a fraction of the strip material that we can observe in other wavelengths. In my case, for example, I started a PhD and I'm starting to learn about radio data to trace the gaseous tails, and I think many of us here might be a little bit biased towards any sort of gas tracing wavelength, but we shouldn't be quick to disregard the optical images because, of course, they provide insight about the star formation, but also they are vastly available. So what we may lose, we don't look at all the iceberg, but we get more numbers. So the question that follows would be, is this fraction of the iceberg enough? Like, can we identify the tail from the optical images? And the answer to that is yes. This is the main result of our work, where we measure the tail directions with respect to the center of the cluster of a large sample of jellyfish candidates, finding that most tails tend to point away from the cluster center, finding this monotonically decreasing distribution, which would be consistent with these jellyfish galaxies being a population mostly following in falling radial orbits. Now, we can further use these results to constrain the lifetime of the tails, and we do that by using cosmological dark matter-only simulations, together with, to which we then add tails artificially following a set of free parameters that determine when the tail appears and disappears. So the idea is to find the parameters that match the observations that we get. And for that, we use Bayesian parameter estimation, finding that optical tails appear at 1.16 virial radius and can be visible for 650 megayears after pericentric passage, leaving us with a very nice constraints about the timescale of the tails, which tells us that ramp pressure stripping is quick to act as a galaxy moves through the intracluster medium for the first time, which as well tells us that broadband optical images are indeed useful for studying ramp pressure stripping, but if you are not convinced, you are all invited to go to my poster. Thank you.
Hi, I am Francesco Salvestrini, a postdoc at the Trieste Observatory, and in this work I focused on massive systems at cosmic noon, which is the epoch where both star formation and supermassive black hole accretion peak. In particular, we focus on ALMA and NOEMA interferometric observation of 20 fields where we observe both quasars and sub-millimeter galaxies. This system are very massive, they are placed in very high density site where mergers play a crucial role in sustaining the star formation and to provide pristine gas to form new stars. We use interferometric observation to measure the continuum in order to model the far-infrared spectral energy distribution, which is crucial to determine both the dust properties and the star formation activity, especially in quasars, where we are not able to directly measure the star formation from UV or optical observation. And we also use CO emission lines that we collect in order to compare the properties of the quasars, which are in red in the panel in the upper left side of the slide, with both sub-millimeter galaxies at the same epoch and also at other epoch, and we found that the quasars are always depleted in CO. But this may be an evidence for the quasar feedback, but it can also be an evidence for an enhanced star formation in these objects, because maybe these objects have a peculiar accretion process that fuel the nuclear part where most of the star formation happens, because also these objects have very compact sizes. The effect of the quasars is obviously visible when we look at the excitation of these molecular lines, in particular the CO spectral energy distribution, and this also reflects in the very high star formation efficiency. If you want to know anything, you can ask me. Thank you.
Hi everyone, I'm Ankit, and I work as a research fellow at Korea Institute for Advanced Study in Seoul. And I'm presenting here a poster based on our research that got published a few months ago, which explores the effect of local environment on AGN activity. And as we know that AGNs exist as radiationally efficient or radiationally efficient. And in both the modes, we think of them to be fueled by the accretion of gas onto the central massive black hole. And we know that the supply of this gas can be affected by the environment, as we found out in the talks during this week. And so now the question arises, how does this environment affect the AGN activity? In the observations, we have a lot of observations that support this claim that AGN activity does get influenced, and the others which say it is not so much. And the nature of the observations can be different, therefore it's very hard to compare and come to one conclusion. So we try to tackle this using simulations, where we use Horizon 105 simulation, which is a huge box size of 1 gigaparsec with a resolution of 1 kiloparsec. And we study the effect of the distance to the nearest neighbor and the mean number density around a galaxy. And we found out that environment plays a minor role in shaping the AGN activity. The distance to the nearest neighbor enhances the AGN activity more compared to the mean local density around a galaxy. And the quasar mode AGN contains more cold gas around the central massive black hole, and therefore they are more their AGN activity is more. If you want to know more about the topic and other things, please come to my poster, second from the front.
Hi everyone, I am Wenyan Wu from National Taiwan. I'm an undergrad student from National Taiwan Normal University, and I'm working with Dr. Lin's group at HIA in Taiwan. In this project, I compare the overlapping galaxies from two surveys. MANGA, a spectroscopic survey in the SDSS 4th generation, and HSC, Hyper-Suprime Kin of the Subaru telescope. MANGA provides spatially resolved information that we can form stellar mass maps and star formation rate maps, while HSC only provides five bins of imaging. So the HSC data goes through a machine learning that trains the 5 bins data to output the information as MANGA. Since HSC, the resolution of HSC is 10 times higher than MANGA, I compare the MANGA data with two kinds of HSC data. The lower resolution one, same as MANGA, and the full resolution one. And then I study their quenching modes to see if the results of HSC are consistent to those of MANGA. Since the HSC survey covers much wider sky, if this method does work, we can apply it on more research. So let's see the training results. These are the consistency between MANGA real data and the HSC machine learning data. Those lines are 1-to-1, and we train stellar mass surface density and star formation rate surface densities, which derive from either H alpha or the 4,000 angstroms break. Stellar mass shows better consistency, while the star formation rate outcomes are quite different. We are still working to improve this method, so welcome to see my poster and discuss with me. Thank you.
Good morning, I'm Ariel from the Observatory of Padova, working with these wonderful people organizing the conference. And I'd like to very quickly share with you some of the results that we got analyzing these HST observations of jellyfish galaxies. And perhaps the main result that we get is that as you go further away from the stellar disk, you find stellar associations that are younger, also less massive and less obscured by dust, which is the opposite of what I naively expected when I started to look at the data. And the key to understanding this is that RAM pressure works on gas and not on stars. So when you start stripping the gas, stars form near the disk, and since stars are not affected by RAM pressure, they get locked there. And this, the gas keeps being stripped, forming new stars, and by the time that you observe the full tail, you observe this gradient. But of course, now that I explained it, you have no reason to talk to me during coffee, so let me just leave you with this more controversial result, that the stellar masses and surface densities of the largest stellar associations that we find are consistent with them being the progenitors of dwarf galaxies, just like Veronica Laura showed. So if that got you to scratch your heads a little bit, then I'm satisfied. Thank you.
So before we break for coffee, just some important announcements for today, for at the end of the sessions. If you have any dietary restriction, vegetarian, anything, please go to Federico at the secretary, collect your ticket, which we will put next to your plate, so you will help the people at the restaurant tonight. Please let us know, say at Federico, everybody, if you plan to come with your own car, because then we will not wait for you at the bus this afternoon. Okay. At the end of the session, as we already said, we will finish by 10 to 5 in the afternoon, let's say 5 o'clock. The buses will wait for us in Via Cardinale Maffi. Somebody from the local team will guide you there. It's really 100 meters, so it will be very easy, but to make it even easier, we put the map here, but you know, just follow them, left, and you will be at the buses. The buses leave at 5:15, so be on time, please. When we arrive there, you will also be guided by people, some of us will be guided from where the bus leaves us to the charter house, and then from the charter house to the restaurant, we will be walking. It's 1 kilometer, so it's really a nice walk. But if anybody does not want to walk this 1 kilometer, please tell me. I will have a car, and there will be other cars, so I can pick you up. Just let me know now or at lunch. When we arrive at the charter house, we will divide in 3 groups for the visit to the charter house. Okay, now we break for coffee. Thank you.